Hey guys, Mr. Milton here. Today we're going to talk about proving quadrilaterals are parallelograms. At the end of this video, you should be able to use given information to say whether a quadrilateral is a parallelogram, and you should be able to justify why a certain quadrilateral is or is not a parallelogram. Last lesson we were given that a quadrilateral was a parallelogram, and we concluded certain things about the angles, sides, and diagonals from that information. Today we are doing the converse. Okay, we're going to be given a characteristic, and we need to determine whether the information is enough to say we have a parallelogram. Okay, so instead of being given that we have a parallelogram, we're going to be given other information to see if we can say that it's a parallelogram from that information. Okay, Theorem 1, if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Okay, and so we're going to prove that with this proof. Here, given is that AC and BD bisect each other. Okay, so as we've done, we'll go through this proof. Not necessarily that all your practice will be proofs, but this proof shows that this will work in the general sense. Okay, so writing down the given information now. Okay, so AC and BD bisect each other. And so from that information, then we can say that AE is congruent to EC. And also we can say that DE is congruent to BE. And this is all just a definition of bisect. Okay, bisect means it cuts in half, so since it cuts in half, then those two pieces of each line are congruent to each other. Okay, and that's already marked for us. From there, since we're going to be talking about we need to prove that ABCD is a parallelogram. Sorry guys for skipping that step. No point in starting a proof and not knowing what we're proving. We need to prove that ABCD is a parallelogram. And so what a parallelogram is, remember, is that we have two pairs of opposite parallel sides. So we need to show that both pairs of opposite sides are parallel. Right, just the definition of parallelogram. So what we're going to try to do is show that AB is parallel to DC and that AD is parallel to BC. We'll go through the same kind of triangle proofs that we're going to use, and I think that what we'll eventually be able to do is show that alternate interior angles are congruent, and then if alternate interior angles are congruent, then we can say that the lines are parallel by the converse of alternate interior angles theorem. Okay, so that's the outlook of how this is going to be proved. So far, we've just used definition of bisector, the information that they gave us so far, to say what's written. Alright, so from there then, since we're going to try to prove that these triangles are congruent in order to use some CPCTC, what I can say is that angle AEB is congruent to angle DEC. I'll say CED just so I don't have to think about it later. And also I'm going to say that angle AED is congruent to angle CEB. Basically, that the vertical angles are congruent to each other. So AB, CED, and then AED and CEB. Okay, give those markings. Okay. So from there, I'm going to be able to say that these triangles, in this case, I can say that triangle AEB is congruent to triangle CED, and I can also say that triangle AED is congruent to triangle CEB. Okay, and both because of side angle side. The nice part about getting these markings down, so we can see those. All right, and so what I want to use this for is I want to be able to say that these two triangles are congruent, so their corresponding parts have to be congruent. So I can see that in this triangle, angle BAE should be congruent to DCE. Okay, so these two angles should be congruent to each other. Alright, so I'm going to say angle BAE is congruent to angle DCE. Okay, and that's by CPCTC. Corresponding parts of congruent triangles are congruent. And I can also say that angle, the other triangles that we set up, I can also say that angle DAE, let me say that DAE is congruent to angle BCE. And BCE is here, BCE. Okay. Alright, so I can tell that those two are congruent because of CPCTC. The naming rules allow me to see BCE is the same as DAE. Okay. Alright, now because those are congruent, then I can say that AB has to be parallel to DC, and also that AD has to be parallel to BC. And that is the converse of alternate interior angles theorem. And since those two lines are parallel, we have those two pairs of parallel lines, then I can say my proof statement that A, B, C, D is a parallelogram by the definition of parallelograms. Got a little crooked there. Sorry, guys. All right. Okay, so again, not that we would necessarily have to do that all the time to prove it all the time, but you see that it's true in the general sense. If we're just given that the bisectors are that the diagonals bisect each other, then we are able to prove that it's a parallelogram. Okay, so some other theorems, we're not going to go through proofs of all of them. If one pair of opposite sides of a quadrilateral is both parallel and congruent, then the quadrilateral is a parallelogram. And so how that will look if we have, see if these two are parallel to each other and congruent. In order to connect them, then what we'd have to have is two lines. These next two lines would also have to be really parallel and congruent. But if we know that these two are parallel and congruent, then that's enough for us to prove that the whole figure has to be a parallelogram. Okay. Okay. Theorem 3 will say that if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. I want you guys to draw an example of parallelogram that shows that there. And then in theorem 4, if both pairs of opposite angles are congruent, of a quadrilateral are congruent, then the quadrilateral is a parallelogram. I also want you guys to draw an example of that for me. Okay. All right. So here's some sample problems that you'll run into. Some types of sample problems, or some types of problems you'll run into. First one, find the values for the variables that would make the quadrilateral a parallelogram. Okay, we're given something about diagonals, and so now we have to think, what do diagonals have to do with parallelograms? And you should say, okay, diagonals have to bisect each other in parallelograms. So that means I would know that 2y minus 7 equals y plus 2. Because these are diagonal pieces, these two would have to be equal to each other. And I would also know that 3x equals x plus 5. Okay, and so now I just solve for both of those. Subtract y from both sides, add 7 to both sides, y would equal 9. In this case, subtract x from both sides, divide by 2, x will equal 2.5. Okay, and that's just us knowing that if this were a parallelogram, if x was 2.5 and y were 9, then that would make the diagonals bisect each other, which is necessary for a parallelogram. All right, examples down here. It says, is there enough information to prove that the quadrilateral is a parallelogram? So for number 1, the answer is yes, because remember in our third theorem it says if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So I'm just going to put here right now for space theorem 3. Yes. Number 2, we have a pair of congruent sides and a pair of parallel sides. Is this it? The answer here is no. Okay, remember in our second theorem it said that we needed a side that was both parallel and congruent. In actuality, if we had a pair of parallel sides and a pair of congruent sides separately, it could be a trapezoid. Okay, so no, this is not enough information. Not saying that this is the exact case, but saying that it's not enough information to say that it's a parallelogram. Number 3, looks good, but the answer is no. Okay, notice that these diagonals don't bisect each other. They do cut it into congruent pieces, but in order to bisect each other, that means this side has to be 1 and has to be equal to this side, or 2 be equal to this side. Okay, so no. This is no. It could be a trapezoid. No, the diagonals don't bisect each other. Okay, and then the final one, I'm going to assume that M is a length, and so this would be yes. Theorem 2. Okay, and theorem 2 in this case, I don't want you guys to necessarily remember, oh, that was theorem 1 or that was theorem 2. But I'm writing theorem 3 and theorem 2 here just to save space. You have it on your notes. You can look. Theorem 2 says that if a line or opposite sides are both parallel and congruent, then it's a parallelogram. Okay, so this falls in line with theorem 2. This falls in line with theorem 3. This does not hit the mark for our first theorem, and this does not hit the mark for theorem 2. Okay, all right, so there you have it. Being able to prove a quadrilateral is a parallelogram using some of the characteristics. See it.